There's, so it's time. So Jonas, is coming from Foz do Iguaçu, I think.
Yeah.
And he's presenting from there, from Brazil, something about Itaipu, I think. So
Yeah.
it's a presentation about a dynamic equivalent model for testing the Paraguayan-Argentinian interconnected power system devices using hardware-in-the-loop simulation. So it's going to present in English. So let's go ahead, Jonas, and it's all yours.
Thank you very much. Yeah, I am located in the border between Brazil and Paraguay, and we are doing a lot of work actually involving including the Uruguayans. In this time, right now, we are also in another meeting with the Argentinian, Paraguayan, and Uruguayan fellows, because there is this interconnection between the power systems that are going to take place maybe in the next months or even years. So this work is in this context. As said, my name is Jonas, and it's a pleasure being with you in the 2021 Urucon. This work was performed for testing devices in a hardware-in-the-loop fashion to evaluate their performance in order to ensure helping the safety operation of the interconnected Paraguayan-Argentinian and, of course, Uruguayan power systems. We're going to be together in the next years, I hope. And first, the protection functions evaluated was related to the power system dynamic phenomena. So it's crucial to represent the dynamical phenomena with high accuracy once we are going to test it. Second, the hardware-in-the-loop testing equipment that we have present a limitation of the number of elements that can be represented, usually tens of elements. And so it's mandatory to reduce the system that we are going to simulate to enable this representation in the hardware-in-the-loop equipment. In this specific case, the original power system that we have modeled that has almost 4,000 elements, and our equipment has a limitation of about 100 elements. So our work was to reduce these 4,000 elements to around 100 and preserve the dynamical phenomena on the proximity of the tested elements. And the context that I said of the development of this work is that there is a planned interconnection among Paraguayan-Argentinian and, of course, Uruguayan power systems for the short-term operational horizon. And to enable this interconnection, a 500 kV, 300 kilometers transmission line was built, and other deployments such as current transformers, protection switches, among other equipments were also performed. For the safety operation of this interconnected system, a special protection scheme was developed to assure system will be stable after large disturbances, and also 2 out-of-state protection functions were enabled to perform the special protection scheme backup, and this protection needed to be tested. And the power system reduction was performed by the following steps that are presented in these slides. First, definition of internal and external areas. The external will be reduced and the internal will be preserved because the phenomena will be measured on the elements on this portion, the internal portion of the power system. And the internal area for our system is the most of Paraguayan elements, Itaipu and Sereta power plants, since most of the device tests are installed on these elements. And the external area is the Argentinian power system, since we are not involved on deploying devices there. And the Uruguayan power system, so it is the same. The identification, the second step is the identification of the current generators that can be aggregated to a single generator, and its dynamical behavior will be preserved. And the third step is what we call the static network reduction, and the elements that does not perform dynamical phenomena can be reduced to single elements. And finally, the dynamic aggregation first of the generators reduced to compute the parameters of the equivalent generators, and the controllers which deals with to compute the terms of the equivalent controllers of each family that represents the controllers of the current generators. This step is made by computing the aggregate frequency response of the group of the controllers using the weighted nominal power of each generator for the AVR, governor, and PSS. After obtaining the aggregate frequency response, a least square error routing is computed to obtain a transfer function that represents the aggregated frequency response. And we selected four steady-state cases for the simulations in the loop fashion, and which are the most representative of critical conditions, and combines low and high Paraguayan load and low and high power interchange between Paraguayan-Argentinean power systems. They are shown in that slide. And the identification of the current generators was made by analyzing power oscillations based on the linearized model of the power system. This figure on the slide represents the mode shape by its module and phase for the dominant mode of oscillation, where it can be seen that Itaipu and Yacireta that are internal generators of the model oscillate against for groups of generators composed by Argentinian generators. So there is this separation, or maybe you can say energy interchange between these two power systems. And these four groups of generators of Argentina can also be grouped in one generator, and it will be increasing furthermore the reduction of the power system and still preserve the dynamical phenomenon that we want to see. This is a reduction that we did obtained by applying these four steps presented on the slide 4, resulting in a reduction of almost 40,000 buses to 22 buses, more than 2,500 transmission lines to 28, and so forth. Concluding this, there was a significant reduction of the size of the power system, which impacts the computational burden also, as presented in the slides. For this illustrative case, we are running simulation of about 40 minutes, and we lower down it to a little bit more than 1 second. So there is a big difference between the two models for the simulations. From the point of view of small signal stability of the linearized system, the representation of the modes of interest was considered very good indeed. In this slide, the dominant mode for the controlled system is presented, where it can be seen an excellent correspondence of the mode frequency, 0.31 hertz in the worst case, and also a very good result on the damping also. So we were looking at the same modes in the equivalent system and also the whole power system representation. Continuing comparing the time-step simulation of largest numeracy, the correspondence between the simulation of the full system and equivalent system representation showed also an excellent proximity between them. In this slide, the response of an opening of a 500 kV transmission line after a 100 milliseconds short circuit without system controllers show the structural nature of the dynamic elements the system is preserved. We can see on this oscillation that is almost the same in the equivalent system and in the whole system representation. And following the last slide, this slide response of an opening of 500 kV transmission line after also a 100 millisecond short circuit. I think it was the same disturbance that we have simulated. But in this case, we are considering the system controllers, and we are seeing also a very good representation of the equivalent system when compared to the whole power system. And this 22 bus model was implemented then in what we call the real-time digital simulator, also known by RTDS, to test the protection relay of the transmission lines that interconnects Paraguay and Argentina, which are called Jonas, Yacireta 1 and 2. And the out-of-step protection functions were evaluated through 214 events, considering several fault locations and 4 power flow conditions that I showed before. And this schema was chosen for the backup of the special protection scheme because it has some features. One of them is they uncount the axis crossing and impedance leaving the protection zone, which is very common on the PPS or out of step protection functions. It also allows to count the impedance trajectory entering non-protective zone. It is important because, as we have considered many different disturbances, some stable dynamics can occur in a way that the electrical center does not develop inside the transmission line, which is the very common situation. So we had this particular situation that we can deal with this type of feature of the protection. In this protection, this function that we had available also allowed to count more than one entry during a power system event. This feature is important because it enables to meet the coordination needs of the special protection scheme and other existing protection in the power system. So it was very good that we had this function available. And by implementing this equivalent system in the RTDS equipment, we could compare the response of the both power system, the equivalent one, and also the RTS run a type of simulation that we call detailed, three-phase detailed. So it's two different types of running simulations with the whole system is simulated in a phasor-based simulation. So when we compare these two responses, we saw a very good correspondence on the impedance that the protection were seeing. So we are very pleased to see that, as presented on this slide by the light gray line is the response for the complete model, and the dashed black line is the response for the equivalent model. And also, I am presenting something about the coordination of the functions. In this slide, we had this special protection scheme actuating very fast, something about less than 400 milliseconds or so, 200 milliseconds most of the case. And one of the PPS, or the out of protection scheme, that is a backup for the special protection scheme, is actuating by something about 2 seconds, and the third special protection, or the second backup protection scheme, is something about 3 seconds. So we had a coordination for the worst case of about 500 milliseconds that we consider a good coordination for this type of phenomena. So we can adjust it on the real-time simulations and be assured that the system is, that the devices are coordinated among them. As final remarks, we state that this interconnection between the Paraguayan-Argentinean and, of course, Uruguayan power system is the largest, large-size endeavor, impacting several companies and demanding to assure devices deployed to ensure power system operation safety will be good. So we had to test it, and one of the tests that we had to do was to develop a system equivalent, which was presented on this work. This equivalent show, in our perspective, a very good representation of the phenomena of interest and a significant reduction of the power system elements and computational burden also. The equivalent system was used to test protection function on hardware in the loop fashion, helping to solve some issues and helping also to define the adjustment of these functions. That's all. Thank you very much for being with me. I am open to chat or something like that.
Okay, thanks a lot, Jonas. Let's see if there's any questions in the chat area.
Cannot see none.
No, I cannot. I have a question. So you were talking about that one of the steps is the Uruguayan is also working to work with this, right? That the interconnection between the Uruguayan system too. Is that already taking place, or is it going to be later? And is that affecting your model? You have to take into account the interconnection with the Brazilian also. I mean, it doesn't say here about the Brazilian, or it's just something that it's only for. I mean, it doesn't affect too much.
Yeah, thank you, Enrique. Very good question indeed. So, this interconnection is taking place at this period. We are working in a lot of tasks right now. Indeed, we have some field tests foreseen for the next weeks. So I think we are going to do a lot of works in the next weeks, and we are also already considering the model of the Uruguayan power system integrated to the Argentinian power system. So some phenomena that we of the disturbance that we simulate, we see also happening in the Uruguayan power system. And you have also, of course, a big power plant divided with Argentina. So we are simulating the dynamic of this power plant too. But in the when we speak about the Brazilian power system, we are kind of separated from the Brazilian power system because we have this HVDC transmission between the system, and it kinds of the cope this power system. We have I think, an interconnection of Uruguay and Brazil in south of Brazil. I and also one with Argentina, which I think is gotta be. And also we have one here between Paraguay and Brazil power systems, which is the Furnas HVDC. But this the nature of these devices, this HVDC, um, allow us to not to represent the Brazilian power system. It does not affect it too much the model of the disturbance that we simulated. But we are also integrating these both simulations in the next what we call the our base of studies, or integrated model. I don't know if I go through all the things that you
Okay, oh, that's
that
nice. Thank you. I think it's a lot of work if you have to really see the interconnection or the effect, how the Brazilian system affect, but that's bigger one. Uruguay and maybe it's a little bit small, so the effects may not be so big, but in the case of the Brazilian will be probably much more important if there were something, right? Okay, so let me thank you
thank
and
you.
well, wish you good luck with all this modeling and the facts that you should work well with the system.